Hey guys, this is Mr. Ainsworth. We're going to get into lesson 3 here and talk about how to solve differential equations of the first and second order. So we ought to start off by talking about what in the world a differential equation is. All right, what is a differential equation? Well, it's simple. A differential equation, DFEQ for short, a differential, all right, equation is one containing a derivative. It's one containing a derivative. Okay, like y prime or dy dx. Okay? Or f prime. I'll put f prime here too. Okay. And one of the things that's unique about differential equations is that the solution to it is not a real number. Okay, is not a real number. It's actually a function. Okay, so the solution is it is a function now. A function. Call it y equals some function of x. Y equals f of x. So that's a real big difference. You know, before we solved equations, we got real numbers as answers. Now, when we solve differential equations, we don't end up with a real number at all. We end up with a function, y equals f of x. And that famous constant of integration that you solved, or that you saw in the last couple lessons, well, we're going to be able to find it today. If we are given what are called initial conditions here, which I abbreviate as IC, okay, initial conditions, it is possible to find the constant of integration. Okay, well, that was the bell. Okay, so let's get right into it. Let's solve a differential equation of the first order and step it out on the left. Okay, first of all, notice our differential equation right here. Y prime is 3x squared. We're looking for a function whose derivative, y prime, is equal to 3x squared. You probably can think of one in your mind right now. Okay, what function do you differentiate to get 3x squared? So think about that as we do this here. But also passes through the point y equals 1, excuse me, y equals negative 1, and x equals 1. This actually is a point, okay, and it's 1 comma negative 1. This is called the initial condition, okay, right here. So what we're going to do is we're first going to write, step 1 here, is we're going to write y prime as dy dx. And the reason why we want to do that is because we're going to separate variables in a minute. Okay, so here we go. We're going to take this and we're going to work with it here. We're going to take y prime and write it as dy dx, because our variable's in respect to x over here on the right, 3x squared. Step 2, we're going to separate variables. Okay, we're going to multiply both sides by dx, and we get dy is equal to 3x squared dx. Step 3, we're going to integrate both sides. Okay, and so I'm going to take the integral of dy and the integral of 3x squared dx, both of which you can handle now. Now, the integral of dy can be thought of as the integral of 1 dy, so the function is 1. So you need to be thinking of a function whose derivative is 1. Okay, and in respect to y, so we're looking for a function of y now, whose derivative is 1. And the answer to that question is y. Okay, the derivative of y is equal to 1. Plus some constant of integration, we're going to call it c1, because both integrals are going to involve a constant here. So a constant from the first integral and then a constant from the second. That's going to be equal to the integral of 3x squared dx. Now we're looking for a function whose derivative is 3x squared, and that's x cubed. Plus another constant of integration, I'm going to call it c2. Now I want to solve for y, because our solution is a function now, so I'm going to subtract c1, and I get y is equal to x cubed, and then c2 minus c1, a constant minus a constant. Remember, these are both constants here. A constant minus a constant, and you get another constant, so I'm going to call it c3. in the future, you're not going to see me put constants on both sides. All you're going to do is you're going to see me put a single constant on the right, because whenever we gather constants, they form another constant. Okay, so you're just going to see me in the future write y equals x cubed plus some c value. I'm not going to even put c3. I'm just going to write a c as for my constant there. All right, but I want you to see how it's generated here. Actually, both integrals produce a constant, but when you gather them, you get a single constant, because a constant minus a constant is just a constant. Okay, great. So now what we need to do is we need to make sure we find C3, the constant. So what we're going to do now is we're going to use the initial condition to find the constant. So step 4 is use the initial conditions the ICs, to find the constant. Okay, now I know the initial condition for us is x equals 1 and y equals negative 1. So what we do is we substitute them in there and we find the value of c. Okay, so y I know is negative 1, x is 1, and I got to solve for c. So 1 cubed is 1, subtract 1 from negative 1, and you get negative 2 equals c3. Okay, and the last, step, it would be to actually write the equation. So I'm going to take this and just substitute it back so I can write the function. So step 5, substitute the constant in and write the function. Now let me write it down that way. So substitute the constant once you find it in the function. Substitute the constant in the function, okay, and write function. Okay, so here we go. Everybody, all eyes up here. So what we're going to do is we're going to say y is equal to x cubed plus c3, but c3 is negative 2, so minus 2. This is my solution. Okay? And how do you check it? Well, you differentiate it. Okay, so you want to check by differentiating. Okay, and you should get the original derivative. Okay? And that should be 2. Y prime is equal to 3x squared. And if you want to check that equation and see if it passes the point, you can do that too. But I know it does. Okay? So there you go. We're looking for a function now and not a real number. Now there's one possible way to do it. But let me show you a different way to write it. Because one of the things in calculus that you have to realize and get used to is that in calculus there's more than one way to do it, more than one way to write it. So let me show you a different way. Instead of separating variables, we're just gonna take our equation here, y prime equals 3x squared, and I'm just simply going to integrate immediately. Okay, so I'm going to integrate y prime dy, and I'm going to integrate 3x squared. Now it's in respect to x, so I'm going to put the dx there. When you integrate y prime, because it's the inverse operation, it gives you y. Okay, plus some constant, but I'm going to put the constant on the right. And then when you integrate the 3x squared dx, you're going to get x cubed, plus some constant of integration. Okay, so you could, if you like, do it this way, or write it this way, because it's the same but just written slightly differently. And then, of course, you substitute your ICs in. Okay, y is 1, negative 1, x is 1. Isolate, you get negative 2 equals c. And then you take this and you substitute it back, and you get y is equal to x cubed minus 2. And you're done. So you could show your work that way too as well. Just keep that in mind. There are a couple of different ways you can do it. Okay, so now let's take a look at another example here. Let's take a look at y prime is equal to x squared times root y. And let's solve for this one, knowing that it passes through one Okay, so what we have here is y prime is equal to x squared times root y, and what we need to do is go through the steps that we illustrated on problem number 1. We're going to change y prime to dy dx. Okay, I'm going to try to resume this video once more. Here we go. I'm going to change y prime to dy dx so I can separate variables here, because I got x's mixed up with y's, and that's no good. So I have x squared here times root y, or y to the 1/2. Okay, I don't want to separate variables, so I want the x's on one side, the y's on the other side. So I'm going to first multiply by dx, and I get dy is equal to x squared y to the 1/2 dx. And I want the y's grouped up together because I want to integrate them independently. So I want to divide by y to the 1/2, and I get 1 over y to the 1/2 dy is equal to x squared dx. Okay, and I want to integrate both sides right here. And before I do on the left side, I want to rewrite it as y to the negative 1/2 dy is equal to the integral of x squared dx. Now I'm ready to integrate, because now all we have to do is use the power rule, and then be pretty straightforward. Now both integrals produce a constant, but I'm just going to write one constant on the right, because after I gather them, they're only going to be one constant. Okay, there's only going to be that. So let me see, I add 1 to the exponent, so I get y to the negative 1/2 plus 1 divided by negative 1/2 plus 1 is equal to x to the 2 plus 1 divided by 2 plus 1 plus c. Okay, and I want to simplify that, so I get, let me see, right here I get y to the 1/2 divided by 1/2, and that's 2y. And then I get x cubed divided by 3 plus c, or 1/3 x cubed. You can write it either way. So at this point, this is your general solution here. Or if you divide, well, you could divide through by 2 if you want. Wait a minute, I didn't write it down correctly here. Something happened. Y to the, oh, it's not 2y. It's negative 1/2 plus 1 is 1/2. So this is 1/2 here. So there we go. Or 2 times root y is equal to 1/3 x cubed plus c. This is called your general solution, okay? But we want a specific one for this problem, because I know that the curve passes through 1, 0, and that's called your initial condition. So when x is 1, y equals 0. That's what that means. And so what I need to do is substitute in the IC to find c. So I'm going to substitute 0 in for y. So we need to find the constant here, find c using, okay, the initial conditions. Okay, so here we go. I'm going to substitute 0 in for y and then 1 in for x. So I get 2 times root 0 is equal to 1/3 times 1 cubed plus c. Well, that 0 equals 1/3 plus c, so c equals negative 1/3. Okay, and then all you do is substitute that back in. You substitute that back in. No, right up top here, right there, and you'll get your specific function. So my solution now, as a function here, is 2 times root y is equal to 1/3 x cubed minus 1/3. Okay, and that is my solution to the problem. So let's highlight that. Okay. There we go. All right, so let's try this just one more time, just to get the hang of it here. In number 3, we have this differential equation that looks like y prime is equal to x times the root of 1 plus x squared. And we know it passes through 0, negative 3. So there we have our initial condition right there. So now notice there are no y's involved on the right-hand side. So what I could do is I can, I can do one of 2 ways. I can rewrite y prime. In fact, I'll do it both ways so I can show you, because there are 2 different ways you can write this. Okay, so based upon what I said in my first example, I'm going to rewrite y prime as dy dx. Okay, and I get x times the quantity 1 plus x squared to the 1/2 power, so I can rewrite it exponentially. I'm going to separate variables, so I get dy, just dy, is equal to x times the quantity of 1 plus x squared to the half power dx. Now I want to integrate both sides. And what I get, and remember that on the left-hand side, the function here is really 1, so you got to be thinking, the derivative of what function gives you 1? Well, it's got to be y. We saw that before in the previous example, so this is going to produce a y and plus a constant, but again, I'm going to gather the constants on the right-hand side. And that's going to be equal to this integral here. Now, this right here requires u substitution because you cannot distribute through the x through the binomial because it's being raised to the half power. All right, so we're going to have to let u equal to 1 plus x squared. So I'm going to do that off to the right. Let u equal to 1 plus x squared. Use u substitution. Du is equal to going to be 2x dx. And I'm going to isolate my x dx because I see x here and dx here. So x dx is going to be equal to 1/2 du. So divide both sides by 2, I get 1/2 du is equal to x dx. So this portion right here is going to be a 1/2 du. And then of course I've got u to the 1/2 in the middle there. So I'm going to rewrite this integral as u to the 1/2, okay, times 1/2 du. Okay, so let's just work with that a little bit. We've got y is equal to 1/2 times the integral of u to the 1/2 to u. I brought that constant on the outside there. I'm going to kick in the power rule and write it as y is equal to 1/2 times u to the 1/2 plus 1 divided by 1/2 plus 1. There's your power rule, plus some constant here. We need to massage that a little bit and simplify it. So 1/2 plus 1 is 3/2. So we got u to the 3/2 divided by 3/2. So 1/2 times u to the 3/2 divided by 3/2 plus c. Okay. And so what we have is we got 1/2 times the reciprocal of 3/2. So 1/2 times 2/3 times u to the 3/2 here plus c. Okay, and the 2's cancel. Okay, and we get y is equal to 1/3 times u, but u is, what's u? Well, let's look above here. 1, it's right here. 1 plus x squared raised to the 3/2 power plus c. There's your general solution. Okay, but I want a specific solution. I want it to pass through 0, -3. So if that's the case, x has to be 0 and y has to be -3. That's called your initial condition. And you need to substitute that in to find c. Okay, so here we go. I'm going to substitute -3 in and go for it here. So we've got -3 is equal to 1/3 times 1 plus 0 squared raised to the 3/2 power plus c. So that's going to be 1 plus 0, 1. 1 to the 3/2 power is 1 times a third is a third. So -3 equals 1/3 plus c. That means -3 and 1/3 equals c. And that, my friends, so this goes right up here. All right, and you write your general or your specific solution. Y is equal to 1/3 times quantity 1 plus x squared raised to the 3/2 power minus 3 1/3. There's your solution. And you got to be happy at that point, man. Okay? So there you go. I know it's fast, it's a video, but hey, go ahead and rewind it, fast forward it, whatever, pause me, slow me down, and then practice it. Repeat this problem over and over again until it becomes easy for you. Again, you're going to have to use u substitution on this problem to integrate. Okay? Substitution. Okay, now let's take a look at a second order differential equation. Okay, and we got some new notation to get used to as well. So all eyes right here. This is what's called a second order differential equation. Your d, okay, it's the second derivative of r in respect to time. So just so you know, this notation right here is synonymous with r double prime. Okay, so it's the second derivative of r in respect to t. Okay, and that's going to be equal to 2 divided by t cubed. Okay, given this initial condition here, this is your first one, IC number 1, that the first derivative r prime equals 1 when t equals 1 there. Let me see. Yeah, t equals 1. This is supposed to be an equal sign right there. And then the second initial condition here, we'll call it IC number 2. All right, here r1 equals 1. All right, that's actually a point, 1 comma 1. So when t is 1, r1 equals 1. Okay, so how do we do it? Well, we integrate twice. So if you're given a second order differential equation, you're going to have to integrate twice. So here's how you do it. You're going to integrate the second derivative, or r double prime, okay, in respect to t. And you're going to integrate the 2 divided by t cubed in respect to t. Okay, now the integral of r double prime is r prime. Okay, how do you write r prime? Well, you write it as dr dt. dr dt. Okay, and that's going to be equal to this over here. Now, you want to rewrite this exponentially, so let's do that. Let's rewrite it first. So 2 times t to the negative 3 dt. So we can take the integral of it, or integrate it easily. So you can bring the 2 out if you want. So it's going to be 2 times the integral of t to the negative 3 dt. So we're going to take t to the negative 3 plus 1 divided by negative 3 plus 1, and then add that general constant. So let's, oops, this is dr, excuse me. Let's simplify what we have. So dr dt is equal to, let's see, 2 divided by negative 2, that's going to be negative 1. And then this t to the negative 2 power is going to shift downstairs, plus some constant here. Okay, now this is where we find the first constant right here. Okay, use your first initial condition right here. So use IC number 1, the initial condition, to find C. Okay, so what do I mean? I'm talking about this one right here, IC number 1. So I'm saying that dr dt is equal to 1 when t equals 1. Okay, so this is equal to 1 when t equals 1, so negative 1 over 1 squared plus c. So you just substitute that in. So the first derivative, r prime, is equal to 1 when t equals 1. So substitute those values in and simplify it. So you get 1 is equal to negative 1 plus c, and this is really tough stuff, and you get negative 2 equals c. So at this point, I know that c is negative 2, and that goes up here. So let me rewrite it here. I got dr dt is equal to negative 1 over t squared plus c, but c is negative 2, so I got to write it as minus 2. Now, I'm trying to find r of t, and right now, I've got r prime. R prime is equal to negative 1 over t squared minus 2. But this is still a differential equation because it involves the derivative. So you have to integrate again. Okay? So if you have to integrate again, go for it. So let's integrate both sides in respect to t and see what happens. Okay, so here we go. The integral of dr dt is equal to the integral of negative 1 over t squared minus 2 dt. Okay? Now the integral of r double prime was r prime. And when you integrate r prime, you get r. So this becomes your r of t. Okay, so r of t here, or just simply r, is going to be equal to whatever the integral of this is. So let's rewrite this before we do it. So we got the integral of negative t to the negative 2 minus 2, all right, dt. Now let's integrate that. Okay, so we got negative t to the negative 2 plus 1, which is negative 1, divided by negative 1, minus 2t. The reason why is because we differentiate that, we get 2, plus some constant right here. let me simplify that. R is equal to t to the negative 1. Oh, I should write that as 1 over t. So 1 over t minus 2t plus c. Okay, so what I need to do is find c again. So what do? Well, I use my second initial condition right there. So use initial condition number 2 to find c. Okay, what is my second initial condition? Let's look up top. Well, it says right here r of 1 equals 1. So let's write that down. R of 1 equals 1. So remember, t is 1 here. So I need to substitute 1 in for t, and then substitute 1 in for r. Okay, so this becomes 1 equals 1 over 1 minus 2 times 1 plus c. That equals 1 minus 2 plus c. That's negative 1. Add 1. So you get 2 equals c. And let's see here. Hang on for a second. Let me just double check something here. Let me stop for a second and check. 1, 2. Okay, you know what I just noticed is that I was looking here and something fell a little bit wrong, so I'm going to have to go back up here and find a mistake, and you probably already noticed it earlier. It's right here. I got to fix this, but that's okay. It's an easy fix. I add 1 to both sides, and so 1 plus 1 gives me 2, so my mistake was right here. I got to fix that, and then fix this here, and just go ahead and go through it. Fix that here, and here, and here, all the way through. It's an easy fix, here and here. And so this is not the case. What we have, when we add 1 plus 2, you get 3. Subtract 3, you get 1 minus 3 is negative 2, and negative 2 equals c. So this value goes right up here. Substitute back. Okay, so my final solution after I fixed my mistake was the following here. Final solution was r is equal to 1 over t plus 2t plus, minus 2. Let me just fix that. Okay, so minus 2 here, and there's your specific solution right there. Okay, this was my general solution, and this is my specific solution here. All right, so lots of fun here, guys. You're going to have to work on this one and get used to it. Get used to the notation, the steps, and how to use your initial condition. So give your homework a shot. Come prepared tomorrow, and I'll see you then.